My name is Rachel Watson. I'm a second year in the Chemical and Biological Engineering department here at Northwestern, and I'm going to talk to you today about making plastic from gas. So, these pictures at the top. What do our very own Shed Aquarium here in Chicago, a pair of shoes, and a bank have in common? Well, if you look closely, they all have examples of a material known as plexiglass. The chemical name for plexiglass is polymethyl methacrylate, or PMMA for short. It is a very strong, clear plastic material, and therefore it's used commonly as a glass substitute. Because glass breaks, and when it does, it shatters, which not only makes it a huge mess, but also dangerous. So having a strong shatter-resistant material is very valuable, and therefore it's everywhere. Again, it's used at the Shed Aquarium because it's strong enough to resist the pressures of even deep waters while still allowing us to see the fish that we came to see. It's so strong, in fact, that specialty plexiglass can even withstand a .44 caliber bullet, which, according to Dirty Harry, is the most powerful in the world. Which is why it has become a staple of bank and post office construction. And, as we saw, it's fashionable and highly decorative, especially since it comes in colors. But what is it? Again, its chemical name is polymethyl methacrylate. The poly here implies that it is part of a group of materials known as polymers. Now, polymers is a broad classification that just means it is a network of molecules all bonded together to form the 3D structure. Another polymer that you might be familiar with is polystyrene, which is used as a packing material, which has opposite properties of plexiglass. It's opaque and very soft. And the reason for this all comes down to the single molecule monomer. For plexiglass, this monomer is methyl methacrylate, and it's different for polystyrene. This monomer is by itself a clear liquid. Going from the clear liquid to our larger polymer structure is very well established in industry. We've been doing this for years. We have this, we got it covered. The hard part, surprisingly, is actually just getting to the monomer. It's very challenging. It takes 3 very nasty steps just to get to this one molecule. We start with something called acetone that you may recognize as nail polish remover. To it, we add hydrogen cyanide, which is nasty. It's flammable, highly toxic, and a terrible pollutant. Then we have to add concentrated sulfuric acid, which is equally dangerous as a pollutant, and it's highly corrosive. Then to that, we have to add methanol, which again, flammable, toxic. All before we can get to our monomer. But we don't just get the monomer, we also get equal parts of side project, sodium, which didn't show up, but take my word, we get a lot of ammonium sulfate out, which is used as a fertilizer and also as an herbicide, which, again, can wreak havoc on the environment. Not to mention, all of this is done at very high temperatures, very high pressures, which industrially speaking, not only makes it very dangerous, but very expensive. And this would be, not terrible, except that it is done on a tremendous scale. Because the monomer, methyl methacrylate, is used globally for a variety of industries, not just our acrylic sheet. Plexiglass is actually only about 32% of the total use of this monomer molecule. The demand is increasing so much, 3% per year, that by 2017, we're going to need to be making 3.2 million tons of this just to keep up with demand. Which also means that if we keep going the way we are, that's 3.2 million tons of the flammable, toxic, corrosive pollutants as well. So what if we didn't have to do that? What if we had a different route? What if we could do this in only 2 steps? Whereas, yes, there are still some problems, so flammable and toxic, but it's cut it down in half. What if we could also do it in a way that makes it lower pressures, lower temperatures, or cheaper, safer for workers? The question is, how?
how can we get past this first step? And the answer is catalysts. So Louisa started us off strong earlier this afternoon and told us a little bit about catalysts, so I just want to reiterate some of the basics. So the plot to your right shows two reaction pathways. So the reaction in the blue is a reaction without a catalyst, and in red shows using a catalyst. A catalyst is a material that enables a reaction to occur. So as you can see, this energy barrier has dropped significantly, allowing this reaction to progress, either where it wouldn't have at all, or at a lower energy cost. Typically, they are metals, as Louisa told us about platinum and iron. I'm specifically looking at metal-containing powders. For example, this powder contains both molybdenum and cobalt. The key is finding the right material to use, and that's where my research comes in. So I take these materials and I test them with this alternate route that I showed at a much smaller scale than 3 million tons in my reactor that's about this big. And I add my ethylene and CO gas and my catalyst that I'm testing along with water to hold it all together. I seal it up, heat it, let it run, and then see what products I get out. And I do this in an effort to find the material that will make the best products with the fewest amount of side products. So I test material after material until I can better understand which ones perform the best, along with looking at other reaction conditions. By doing this, by understanding how materials affect the product distribution, I can design my own materials that will one day lead us to make this alternate pathway an industrial reality. That way it's just a quick hop, skip, and a jump down to our plexiglass. That way we can all enjoy the same strong, great material, but from a cheaper, safer, and greener source. Thank you.